Welcome to the viewers for the lecture in the subject structural analysis. This is lecture number 162, in which we are going to discuss about the analysis of building frames subjected to lateral loads. As we have discussed in the earlier lecture 161, we have three methods. One is portal method, second is the cantilever method, and the third one is that of the factor method. Now, the cantilever method will be discussed in this topic. Cantilever method, yes. And a method will be discussed with the simplifications and the shortcuts, because it's a very simple method that can be used for any number of stories, any number of bays. But when you look at the calculations and when you look at the figures in various books, you will find it difficult, but it is not at all difficult. So first of all, let us simplify the problem, and then we'll discuss about the method of solving the problem, right? So what we do here is, first of all, the method is made as statically determinate. That is, what we do here is, we assume points of contraflexure at the midpoints of columns and beams. That means we are going to introduce hinges at the midspan of beams and mid heights of columns. With this, with one more assumption, we will make the structure determinate. That is, we calculate the overturning moments. We locate the vertical centroidal axis, for which we will find out the factors, and thereby we will straight away calculate the loads in the columns. That will be clear when you listen to the numerical example. Once we find out the moments in the columns, the second part is very simple. First part involves some few calculations. Second part is very simple. It can be straight away completed. The problem, the bending moment calculation, the drawing of the bending moment diagram can be done with minimum simple calculations, but we'll discuss the detailed calculations, how to do it also we'll discuss, and then we'll draw the bending moment diagram. Right? We'll first simplify the problem. Problem is very simple. Use of only the equations of equilibrium. Only after making the structure statically determinate, it is only a question of using the simple equations of equilibrium, namely sigma v equals 0, sigma h equals 0, and sigma m equal to 0. Right. Now we'll discuss the method through a numerical example. Using the cantilever method, analyze the building frame subjected to horizontal forces as shown in the figure and sketch the bending moment diagram. Same problem that we have taken in the portal method, the previous method, we'll take here also, so that you can just compare the values at a later stage. Right? Same example, therefore I am not going to discuss the dimensions, loads, etc. Right. Now, we introduce hinges at the mid span of beams and mid heights of columns. So we introduce, as I discussed earlier, we assume 10 hinges. That is, 2 hinges in the top beam, 3 hinges in the top panel, similarly bottom panel, 2 in the beams and 3 in the columns. So we assumed 10 hinges. We know that a 2-bay, 2-storied frame is 12 degrees indeterminate. The introduction of 10 hinges will reduce the indeterminacy from 12 to 2. Now it is 2 degrees indeterminate after the introduction of the hinges. How to make it determinate further, we will discuss. Right. So this is the top story. The purpose is we are going to find out the overturning moment, this lateral force will cause overturning moment. Overturning moment we are going to calculate at the center of top level. I mean O1, O2, O3 at center of the top story. We are going to calculate at this level, so that the moment will be 60 into half the height is 1.75. Also, we are going to calculate the overturning moment at this level O4, O5, O6, whose moment will be equal to 60 into this is 3.5 top story plus half of the bottom story 2.5. So 60 into 6 plus 40 into 2.5. That will be the overturning moment at the level O4, O5, O6. That is overturning moment at this level due to the loads above this hinge. That we are going to calculate. So that is, before going through calculations, we will discuss some basics. The building frame is subjected to lateral loads, and it is assumed as a vertical cantilever fixed at the base and free at the top. The building frame may be 10 stories, maybe 20 stories, whatever it may be. At the base, it is assumed as fixed. At the top, it is assumed as free. So, in this frame, now it is a vertical cantilever fixed at the bottom, free at the top, subjected to two lateral loads. Right. So, here, the windward side columns will be under tension and the leeward side columns will be under compression. When it bends, the windward side columns will be under tension. Right. There are some assumptions here also, namely, points of contraflexure occur at the mid-span of beams and mid-heights of columns. That is, we assumed hinges as discussed already. Then, next important assumption is the axial stresses in the columns are proportional to their distances from the centroidal axis of the frame. We are going to find out the vertical centroidal axis. So, from the vertical centroidal axis, the nearest column will be subjected to less stress and hence less force. The farthest column will be subjected to maximum force, right? So it is proportional to. So that is why you have to locate the centroidal axis, like you do in the case of centrifugal moment of inertia, A1 x1 plus A2 x2, like that same procedure we are going to use, right? Now, as we have discussed earlier, overturning moment at the level O4, O5, O6, that is at the middle of the bottom story. This we have discussed already. 60 into 6 plus 40 into 2.5. Overturning moment at the middle level of the columns of the top story. Also we have discussed it is 60 into 1.75, 105. So that's about the overturning moment. Now, the cross-sectional areas of all the columns are assumed to be the same. Even if it is different, we can deal with, no problem. So taking moment of areas of the columns about the GDA, about the left side left column, top is G, bottom is A, GDA, about the first one. So A into X bar, A plus, there are three columns, A plus A X bar. If it is different, you have to write it as A1 plus A2 plus A3 into X bar, that's all. Here again, A into 0 plus A into first column, GDA, because we are taking moments about that column. So A into 0 plus A into second row is at 4 meters, the third column is at 10 meters, 4 plus 6. So if it is different, you can write it as A1 into 0 plus A2 into 4 plus A3 into 10. Areas will be known. So here we assume to be the same, that's all. So 3AX bar equal to 14A or X bar equal to 4.67 meters. This point is to be discussed. Yes, 4.67 meters. X bar equal to 4. The center of gravity of all the three will be at 4.67 meters from A. So 4.67 is what we have calculated just now. So remaining value will be 5.33 because total is 4 plus 6 equal to 10. Right. Now here, the first column from the centroidal axis OY, the first column is at 4.67 meters to the left. This is say x1. x2 equal to 0.67 meter because this is 4, so it is 0.67 meter. x2 because we are going to calculate sigma x square, namely x1 square 4.67 square, x2 square 0.67 square, and x3 square 5.33 square. So you must know x1, x2, and x3. So coming to the calculations, this we have completed. Now, axial forces in the columns. After locating the centroidal vertical axis, we have to find out the axial. So, the axial forces are given by a formula Pi equal to Kn into Xi. Because the axial stresses are proportional to the distance from the vertical centroidal axis. Formula is Kn into Xi. For different levels, we have taken two levels, middle level of top story frame, middle level of bottom story. So we have to find out the values of K1 and K2. Here you have to remember that we have taken M1 for the bottom story, M2 to the top story. Therefore, here also in the calculations, K1 for the bottom story, K1 for the, yes, K1 for the bottom story, K2 for the top story. So that you have to remember that order, that is very important, right? Now K1 equal to a constant of proportionality for the columns in the bottom story equal to M1 by sigma x square. Sigma x square, just now I told you, 4.67 square plus 0.67 square plus 5.533 square equal to this value. So M1 is already calculated. Therefore, K1 equal to M1 by sigma x square equal to 9.078. We know P1 equal to K1 into Xi. K1 into Xi. For individual columns, you are going to make use of this formula. Find out the forces for the columns. Column 1, column 2, column 3. You have to use the distance Xi. Suppose if left side column means P1, say, equal to Xi is 4.67. Like that we have to calculate. So after calculating K1, PAD, first column, equal to, this is in the bottom story. We are calculating everything for the bottom. That is only to be remembered. Calculations are simple. So 9.078 into 4.67 tensile force. BE 9.078, the distance is 0.67, is nearer column subjected to less load. So CF is on the other side, namely on the leeward side. So windward side columns will be under tension, leeward side columns will be under compression. This we have to remember and carefully substitute minus to indicate it is a compressive force. So 9.078 into minus 5. So equal to minus 48.39. So this is compressive on the leeward side. Similarly, K2 for the top story, M2 by sigma x square. M2 105 already were calculated, and sigma x square is 50.67 equal to this value. So left side column, first column, K2 is 2.072 into distance is 4.67. This is the tensile force. Second middle column, 2.072 into 0.67 is this value. IF is say for the column IF in the top story is minus 11.04. It is compressive. This you have to remember, minus, and it is compressive force. Right. Now, as far as cantilever method is concerned, the majority of the calculations are over with this. It can be a 10-story frame or 20-story frame or 15 base, no problem. It's a simple calculation, just finding out the in the axial forces. If you find out the axial forces, the rest of the calculations will be shown in the book. You can show the calculations, or even you can straight away explain through the diagrams. The diagrams need not be, confused. They are simple. The columns divided into different free bodies, that's all. The given frame is divided into different elements, that's all. Right. Now, at this stage, we have calculated the axial forces in the top column. You just remember these values. This need not be repeated every time. This is in the bottom story, first column, second column, and the third column. Bottom story, second, third is compressive, right? Right. Bottom story, first column, sorry, this is top story. 9.68, 1.39 tensile, and this is compressive. So these values will be reproduced in the figure. Right. Now first column, 9.68, 9.68 tensile. That is top is divided into two bodies. Up to the hinge, one body, second hinge to the point D, second body. Right. So these are under tension. So we have just marked the forces that we have calculated here. The forces that we have calculated here. Similarly, the second column, 1.39, 1.39. Minus 11 point, this is to be noted. Minus 11.04, 11.04, 11.04. So we have just reproduced the values calculated earlier. Similarly, in the bottom story, these are the values that you have calculated. These two tensile and this is compressive. Right. After this, when you refer to the book, they will say at the joint G, when this is 9.68 downwards, in the column, in the beam, it is 9.68 down, because everywhere you have to satisfy all the equations of equilibrium. If joint G is to be under equilibrium, it has to satisfy all the equations of equilibrium. So here, when it is 9.68 up, this is 9.68 down. Right. So this will be shown in the form of calculations. So on seeing the detailed calculations, one need not fear. Right. So when this, now coming to this free body, when this is 9.68 down, this is 9.68 up. Similarly, when this in the joint, for the joint equilibrium, as it is, there is no vertical force. When this is 9.68 up, this is 9.68 down, because net is 0. And coming to this element, when this is 9.68 down, this is 9.68 up. Similarly, you have to calculate all the forces. Now coming to this joint, when this is 9.68 down, this is 42.38 up. There are two members. So the net force is 42.39 minus 9.68. So that much upward force. Therefore, if the joint D is to be under equilibrium, the sum of all these forces will have to be 0. Sigma V equal to 0. Therefore, the difference will be the downward force here. So that when these three are added, it will be 0. So like this, we have to calculate all the forces. I think the viewers can calculate. We need not spend much time on this. So like this, you have to calculate all the forces. After calculating all the forces, next point is, I have not shown the calculations in the problem. These will be available in terms of words, that's all. Right. Now coming to this, we are going to the next step, namely calculating the moments. Right. Now coming to this element in GO7, 9.68 down, this is 9.68 up. This distance is 2 meters, we know. Top beam. Totally 4 meters, half the length is 2 meters. So these two forces will cause an anti-clockwise moment of 9.68 into 2. So sigma m also will have to be 0. Therefore, this cannot take any moment. The hinge cannot take any moment. Therefore, at G, there should be a clockwise moment of 9.68 into 2. 9.68 into 2. So the 9.68 into 2 is shown here. 682 here, shown here. Similarly, here, in this element, this is 9.68 down, this is up. This will cause anti-clockwise moment. Anti-clockwise moment. Therefore, for equilibrium, you must have a clockwise moment of the same value. The hinge cannot take any moment. Therefore, at H, there will be a clockwise moment of 9.68 into 2. 9. So that is what is shown here. 9.68 into 2. Like that, we have to calculate in all the beams. In the top and also all the beams in the bottom. Here also. Here also we already calculated vertical forces. We have to calculate the moments. The viewers can stop at any stage. Let's surely go through, and these are all very, very fundamental calculations. Therefore, you can understand, right? So we have discussed only about the calculation of moments in the beam, top beam and the bottom beam, GI and DF, right? Now, coming to the columns, we will go to the next diagram, right? Columns. For the column to be in equilibrium, when there is a clockwise moment of 19.36, here it is 19.36 in the anti-clockwise direction. So this calculation need not be shown here. 9.68 into 2 is only for the beam. So 19.36 in the anti-clockwise direction, so that sigma m equal to 0. Because hinge cannot take any moment. Similarly, here also 9.68 into 2. This can be skipped. 9.68 into 2 is only for the beam. Can be skipped. 19.36. So we know due to this moment, the tension will occur on the inner side. Due to this moment, the tension will occur on the outer side. For that you can just understand. So calculate the values of moments in the columns. So coming to this H. Here there is a clockwise moment of 19.36. Here there is a clockwise moment of 32.12. The sum equal to 19 plus 33, namely 52 point something. So when these two are clockwise, for the algebraic sum will give this moment equal to minus 52.48. So that when you add all the three, so you have to write an equation, that is at the joint H, MHO7 plus MHO8 plus MHO2 equal to 0. So that will give you the value of this. Like that only you have to show the calculations. Otherwise, no tedious calculation. Equilibrium equations only. So coming to this column, when this is clockwise, this is anti-clockwise, 33.12. So that is how we will have to calculate. Actually, in both the methods, this method we have discussed earlier and also this method, the axial forces are not given that much. Actually, here we have considered, in the earlier method, we have not considered for the reason mentioned in the earlier problem. I don't want to mix up, right? So this is how, using the equations of equilibrium alone, you have to calculate the moments at various joints. One example of using the equilibrium equation, right? And straight away you can just draw the bending moment. You can just, if you mark, for example, if you consider this moment is clockwise. When this moment is clockwise at G, the tension will occur at the bottom, as discussed in the earlier example. The tension will occur at the bottom. Therefore, you have to mark it down. Say, mark it down like this. So once if you know the clockwise or anti-clockwise moments, you can draw the free body diagram, and bending moment diagram can be easily calculated. So that completes the bending moment diagram for the second problem by the cantilever method. So method assumes the frame as a cantilever fixed at the top and free at the bottom and free at the top. So the leeward side columns will be at a compression and windward side columns will be at a tension. Make the structure as determinate. These calculations, examination point of view, you will have to show it. Otherwise, through this figure, you will be able to do all the calculations. So you have to write it. For a field engineer, this calculation need not be shown. But for students, from examination point of view, you have to show the calculation at joint G. This is the calculation. At joint D, this is the calculation. Very simple, using the equations of equilibrium. So that is about the simplification and also